Trains changed everything. Before 1825, the fastest humans could travel over land was the speed of a galloping horse, about 30 miles per hour. Within a century, trains were traveling at 100 miles per hour, carrying hundreds of people and tons of cargo. The first railways weren't pulled by engines at all. In the 1500s, German miners used wooden rails in coal mines. Carts with flanged wheels ran on these rails, pulled by horses or pushed by workers. The rails reduced friction, allowing one horse to pull what would take 5 horses on dirt roads. By 1604, wooden rails appeared in England at Wollaton near Nottingham. These primitive systems used simple wooden planks. The wheels were also wooden. Iron wheels came later, in the 1730s. Cast iron rails replaced wooden ones around 1767 at Coalbrookdale. The first person to build a working steam locomotive was Richard Trevithick in 1804. His locomotive ran on the Penydarren Ironworks Railway in Wales. It pulled 10 tons of iron, 70 men, and 5 wagons for 9 miles. The journey took 4 hours and 5 minutes. The locomotive worked, but it was too heavy. It broke the cast iron rails. George Stephenson is called the father of railways. In 1814, he built his first locomotive, Blucher, for the Killingworth Colliery. It could pull 30 tons up a hill at 4 miles per hour. But Stephenson's real breakthrough came in 1825 with the Stockton and Darlington Railway. This was the world's first public railway to use steam locomotives. It opened on September 27, 1825. Stephenson's locomotive, Locomotion No. 1, pulled 450 people at 15 miles per hour. The Stockton and Darlington Railway was primarily for freight, especially coal. It still used horses for some passenger services. The real revolution came with the Liverpool and Manchester Railway in 1830. This was the first railway designed exclusively for steam locomotives and the first to carry passengers on a regular timetable. Before the Liverpool and Manchester Railway opened, they held a competition called the Rainhill Trials in October 1829. 5 locomotives competed. The rules were strict. Locomotives had to run 70 miles, equivalent to a return trip from Liverpool to Manchester. They had to average at least 10 miles per hour. They couldn't weigh more than 6 tons. George Stephenson's son, Robert Stephenson, designed a locomotive called Rocket. It won the trials easily, reaching 30 miles per hour. Rocket had several innovations. It used a multi-tube boiler which increased the heating surface area and generated more steam. It had angled cylinders connected directly to the driving wheels. This design became the template for almost all steam locomotives built for the next 150 years. The Liverpool and Manchester Railway opened on September 15, 1830. It was a massive event. The Duke of Wellington, the Prime Minister, attended. 8 trains carried 600 distinguished guests. But the day turned tragic. William Huskisson, a member of Parliament, was hit by Rocket while standing on the tracks. He died later that day, becoming the first widely reported railway fatality. Despite the tragedy, the railway was an immediate success. It was built to transport cotton and other goods between the port of Liverpool and the mills of Manchester. Everyone expected freight to be the main business. Instead, passenger traffic exceeded all predictions. In the first year, the railway carried 445,000 passengers. Investors made enormous profits. Railways spread across Britain like wildfire. By 1840, Britain had over 1,300 miles of railway track. By 1850, this had grown to 6,600 miles. The railways connected every major city. Travel time collapsed. A journey from London to Edinburgh that took 4 days by stagecoach now took 12 hours by train. The social impact was enormous. Before railways, most people never traveled more than 10 miles from their birthplace in their entire lives. Railways made travel affordable and accessible. Third-class carriages were basic, often just open wagons with benches, but they cost only a penny per mile. Railways created new industries and transformed old ones. The demand for iron and steel exploded. In 1830, Britain produced 680,000 tons of iron. By 1850, this had risen to 2.25 million tons, much of it for railways. Coal mining boomed to fuel the locomotives. Employment soared. By 1850, over 250,000 people worked on British railways. Railways even changed time itself. Before railways, every town kept its own local time based on the sun. Bristol was 10 minutes behind London. This was fine when travel was slow. But with trains running on schedules, it became chaos. Railway companies needed standardized time. In 1847, the Railway Clearinghouse recommended that all railway companies use London time, called railway time. By 1855, most of Britain had adopted it. In 1880, it became official law as Greenwich Mean Time. The railway boom wasn't smooth. In the 1840s, Britain experienced railway mania. Hundreds of railway companies were founded. Many were fraudulent or poorly planned. Thousands of investors lost everything when companies collapsed. But the mania did result in a comprehensive railway network that served Britain for over a century. While Britain pioneered railways, other countries quickly followed. The United States opened its first passenger railway, the Baltimore and Ohio Railroad, in 1830. France opened its first railway in 1832 from Paris to Le Pec. Germany followed in 1835 with a line from Nuremberg to Fürth. By the 1840s, railways were spreading across Europe and North America. Early American railways faced different challenges than British ones. America was vast and sparsely populated. Railways had to cover enormous distances through wilderness. American locomotives were designed differently. They were lighter and more flexible to handle rough, quickly laid track. They had larger cowcatchers to push obstacles off the rails. They burned wood instead of coal because wood was abundant and cheap. The American railway network grew explosively. In 1840, America had 2,800 miles of track. By 1860, this had grown to 30,000 miles, more than the rest of the world combined. Railways opened up the American West. Towns sprang up along railway lines. Areas that were wilderness became farmland and cities. Railways played a crucial role in the American Civil War from 1861 to 1865. The North had more railways and used them more effectively. Railways moved troops and supplies quickly. They allowed armies to operate far from their bases. Controlling railways became a strategic objective. The war saw the first large-scale military use of railways, foreshadowing their role in future conflicts. The Transcontinental Railway across America was one of the greatest engineering projects of the 19th century. In 1862, during the Civil War, President Lincoln signed the Pacific Railroad Act. It authorized two companies to build a railway from the Missouri River to the Pacific Ocean. The Union Pacific would build westward from Omaha. The Central Pacific would build eastward from Sacramento. Construction began in 1863 but progressed slowly during the war. After 1865, work accelerated. The Union Pacific employed thousands of Irish immigrants and Civil War veterans. The Central Pacific employed over 12,000 Chinese workers, who made up 90% of their workforce. These Chinese laborers worked in incredibly dangerous conditions, blasting tunnels through the Sierra Nevada mountains with explosives. Hundreds died in accidents and avalanches. The two companies raced to lay track because they were paid by the mile. They worked through brutal conditions. Summer temperatures in the Nevada desert exceeded 120 degrees Fahrenheit. Winter blizzards in the mountains buried work camps under 20 feet of snow. Workers lived in camps that moved with the advancing rails. Everything had to be transported: rails, ties, spikes, food, water, and equipment. The railways met at Promontory Summit, Utah on May 10, 1869. Leland Stanford, governor of California and president of Central Pacific, drove in a ceremonial golden spike to complete the line. The telegraph sent the signal across the nation: done. America erupted in celebration. The journey from New York to San Francisco, which once took 6 months by wagon or ship, now took 6 days by train. The Transcontinental Railway transformed America. It opened the West to settlement. Millions of people moved westward. Towns became cities. Agriculture boomed because farmers could ship their products east. The railway also devastated Native American tribes. Buffalo herds, which Native peoples depended on, were hunted nearly to extinction. Passengers shot buffalo from train windows for sport. By 1890, fewer than 1,000 buffalo remained from herds that once numbered in the millions. Canada built its own transcontinental railway, completed in 1885. The Canadian Pacific Railway connected Montreal to Vancouver. It was even more challenging than the American version. It crossed the Canadian Shield, a vast area of rock and swamp in Ontario. It climbed through the Rocky Mountains, where workers carved ledges into sheer cliff faces. Like in America, Chinese laborers did much of the dangerous work. Over 600 Chinese workers died during construction. Russia built the longest railway in the world, the Trans-Siberian Railway. Construction began in 1891 under Tsar Alexander III. The railway eventually stretched 5,672 miles from Moscow to Vladivostok on the Pacific Ocean. It took 25 years to complete, finishing in 1916. Workers faced extreme conditions. In Siberia, temperatures dropped to -40 degrees. Permafrost made construction difficult. In summer, mosquitoes were so thick that workers wore masks. Despite these challenges, workers laid an average of 400 miles of track per year. The Trans-Siberian Railway connected the vast Russian Empire. It allowed the government to move troops to the Far East quickly. It opened Siberia to settlement and resource extraction. During the Russian Civil War from 1918 to 1922, control of the railway was crucial. Armies moved along it. Refugees fled on it. The railway became the lifeline of Siberia. India's railway network became one of the largest in the world under British colonial rule. Construction began in 1853 with a line from Mumbai to Thane, just 21 miles, but the network grew rapidly. By 1880, India had 9,000 miles of railway. By 1930, this had grown to 41,000 miles. The British built these railways primarily to move raw materials to ports and British goods inland. Coal, cotton, tea, and grain traveled by rail. Indian railways required immense engineering. Workers built bridges across wide rivers. They cut through the Western Ghats Mountains. They laid track across deserts and jungles. Thousands of bridges were constructed. The Chenab Bridge, completed in 2022 but begun earlier, is the highest railway bridge in the world at 178 feet above the river. Railways industrialized India, but also served colonial control. The British moved troops quickly to suppress rebellions. During famines, railways moved grain out of starving regions to ports for export while millions died. Yet railways also unified India. They connected regions that had never been connected. They employed millions of Indians. After independence in 1947, India expanded its railway network. Today, Indian Railways employs 1.4 million people and carries 8 billion passengers annually. Africa's railways were built primarily to extract resources during the colonial period. The Cape to Cairo Railway was Cecil Rhodes's dream, a railway running the entire length of Africa. It was never completed, but many colonial railways were built. The Uganda Railway, called the Lunatic Express, ran from Mombasa on the coast to Lake Victoria. Construction began in 1896. Workers, mostly from India, faced attacks from lions. 2 lions, the Tsavo man-eaters, killed and ate at least 35 railway workers before. They were shot. Australia built railways to connect its isolated cities. Each colony built its own network, often with different track gauges. New South Wales used 4 feet 8.5 inches, the standard gauge. Victoria used 5 feet 3 inches. Queensland used 3 feet 6 inches. This meant passengers had to change trains at borders. Goods had to be unloaded and reloaded. This confusion wasn't fully resolved until the 1990s when a standard gauge line finally connected all major cities. Railways didn't just transport people and goods. They carried mail, newspapers, and information. Before railways, news traveled slowly. A letter from London to Edinburgh took days. With railways, it took hours. Newspapers could be distributed nationally on the day of printing. This created national news media. It helped form national identities. Railways changed how wars were fought. The American Civil War showed their importance, but the Franco-Prussian War of 1870 to 1871 proved it definitively. Prussia used railways to mobilize 500,000 troops in 18 days. France, with a less developed railway network, took much longer. Prussian armies arrived first and won the war. After this, every major power built strategic railways with military use in mind. World War I was a railway war. Millions of troops moved by rail. Supplies flowed to the front lines on railways. Entire economies were mobilized using rail transport. Germany's famous Schlieffen Plan relied on railways to move armies quickly through Belgium into France. When the plan failed and the war became static trench warfare, railways supplied the massive armies. Narrow-gauge trench railways ran right up to the front lines, carrying ammunition and supplies. Railways also became targets. Destroying enemy railways disrupted supply lines. T.E. Lawrence, Lawrence of Arabia, made his reputation attacking Turkish railways during the Arab Revolt. His guerrilla fighters destroyed bridges and locomotives, cutting Turkish troops off from supplies. This tactic became standard in future conflicts. Between the world wars, railways reached their peak. The 1920s and 1930s were the golden age of passenger rail. Luxury trains offered unprecedented comfort. The Orient Express, running from Paris to Istanbul, was the most famous. It had sleeping cars with wood paneling, plush upholstery, and 5-course meals. Passengers dressed formally for dinner. The train carried aristocrats, diplomats, spies, and wealthy travelers. Agatha Christie set her novel Murder on the Orient Express on the train, cementing its legendary status. In America, named trains became celebrities. The 20th Century Limited ran from New York to Chicago. It competed with the Broadway Limited for luxury and speed. These trains had observation cars with glass domes. They had club cars with bars. Some had barbershops and secretaries. A red carpet was rolled out at Grand Central Terminal for 20th Century Limited passengers, creating the phrase red carpet treatment. The Flya Was, Flying Scotsman in Britain, ran from London to Edinburgh. In 1928, it became the first train to offer passengers a cinema car showing movies during the journey. In 1934, another Flying Scotsman, the locomotive Not the Service, became the first steam locomotive to officially reach 100 miles per hour. Its driver, Bill Sparshett, reached this speed going downhill near Little Bytham. Speed became an obsession. In Germany, the streamlined Flying Hamburger diesel train entered service in 1933. It ran from Berlin to Hamburg at an average speed of 77 miles per hour, reaching a top speed of 100 miles per hour. It was fast, reliable, and comfortable. Germany began building high-speed diesel and electric trains. The DRG-class SVT-137 reached 134 miles per hour in 1936, a world record for diesel trains. Britain responded with streamlined steam locomotives. Sir Nigel Gresley designed the A4-class locomotives, the most beautiful steam engines ever built. They had wedge-shaped noses and smooth sides. On July 3, 1938, one of these locomotives, Mallard, set the world speed record for steam locomotives. It reached 126 miles per hour on the East Coast Main Line near Grantham. This record still stands today. The speed was so extreme that Mallard's middle cylinder overheated and was damaged. The locomotive had to be repaired afterward. Steam locomotives dominated railways for over a century. They were mechanical marvels. A typical steam locomotive had over 5,000 moving parts. The basic principle was simple: burn coal or wood in a firebox. This heats water in a boiler. The water turns to steam. Steam pressure builds up. The steam pushes pistons. The pistons turn wheels. But making this work efficiently required brilliant engineering. The largest steam locomotives ever built were absolute monsters. The Union Pacific Big Boy locomotives, built in 1941, weighed 1.2 million pounds, over 600 tons. They were 132 feet long. They had 16 drive wheels arranged in 2 sets of 8. Their boilers could hold 24,000 gallons of water. Their tenders carried 28 tons of coal. Big Boys could pull a 3,600-ton train up steep mountain grades in Wyoming at 35 miles per hour. 25 were built. 8 survive today. In 2019, Union Pacific restored Big Boy number 4014 to working condition. It still runs on special occasions. The Pennsylvania Railroad built 52 S1 class locomotives, the most powerful passenger steam locomotives ever made. They generated 6,500 horsepower. They could reach 100 miles per hour while pulling heavy trains. But they were so large and heavy that they could only operate on the strongest tracks. They were also expensive to maintain. By 1949, all had been retired, replaced by diesel locomotives. British steam locomotives were generally smaller than American ones because British tunnels and bridges were built for smaller trains, but they were highly refined. The Elner Class A4, which included Mallard, represented the pinnacle of steam locomotive design. They were streamlined to reduce air resistance. Their valve gear was precisely timed. They could cruise at 90 miles per hour, burning relatively little coal. Steam locomotives required enormous amounts of labor. A fireman shoveled coal into the firebox, sometimes 10 tons during a single journey. This was backbreaking work. On hot days, the temperature in the cab exceeded 120 degrees Fahrenheit. Firemen often lost 10 pounds of weight in sweat during a shift. Locomotive drivers had to understand their engines intimately. Every locomotive had quirks. Drivers learned to listen to the sounds their engines made, knowing when something was wrong before instruments showed it. Steam locomotives needed constant maintenance. After every journey, fireboxes were cleaned of ash and clinker. Boilers had to be washed out regularly to remove scale buildup. Every few weeks, locomotives went to workshops for detailed inspections. Bearings were checked. Pipes were examined for leaks. Wheels were measured for wear. A major overhaul, done every few years, essentially rebuilt the entire locomotive. Railway workshops employed thousands of skilled workers. Crew Works in England employed over 20,000 people at its peak. Workers made everything from complete locomotives to individual bolts. Apprenticeships lasted 7 years. Craftsmen specialized. Some built boilers, others made wheels. Pattern makers created wooden patterns for casting metal parts. Swindon Works had its own hospital and housing for workers. These railway towns had entire communities built around locomotive construction. Despite their power and romance, steam locomotives had serious drawbacks. They were inefficient. Only about 6% of the energy in coal actually moved the train. The rest was lost as heat. They were labor-intensive, requiring firemen, drivers, and maintenance crews. They were dirty. Smoke and soot covered everything. Cities with major railway stations had perpetual smog. Buildings turned black from soot. Passengers arrived at their destinations covered in grime. Steam locomotives also had limited range. They needed water stations every 50 to 100 miles. They needed coal bunkers or wood yards. Water towers became iconic features along railway lines. In deserts and remote areas, water was scarce. Railways in Australia and Africa built elaborate systems to supply water to locomotives. Some stations in the Australian outback received water delivered by train from hundreds of miles away. Diesel locomotives solved many of these problems. The first diesel locomotive was built in 1912, but early diesels were unreliable. Real development came in the 1930s. General Motors created the Electromotive Division specifically to build diesel locomotives. In 1939, they demonstrated the FT locomotive. It was a revelation. 4 FT units, linked together and controlled by one engineer, could produce 5,400 horsepower. They could run for days without refueling. They didn't need water. They started instantly. Unlike steam locomotives, which took hours to build up steam pressure, American railways switched to diesel rapidly after World War II. By 1960, steam had almost completely disappeared from American railways. The last steam locomotive was retired from regular service in 1961. Europe and Asia transitioned more slowly. Britain retired its last steam locomotive in 1968. China used steam locomotives until 2005. Some developing countries still used steam into the 2010s. Electric locomotives were even more efficient than diesel. They converted about 90% of electrical energy into motion, compared to about 35% for diesel. But they required massive infrastructure investment. Railways had to string overhead wires or install third rails along the entire route. They needed substations to supply power. This was expensive but worthwhile on busy routes. The first electric railway opened in Berlin in 1879, built by Siemens. It was just a demonstration line. The first practical electric railway was the City and South London Railway in 1890, now part of the London Underground. It used electric locomotives to pull carriages through tunnels. The first mainline electric railway opened in Italy in 1902. Switzerland became a pioneer in electric railways. By 1960, Switzerland had electrified its entire railway network. Geography helped. Switzerland generated abundant hydroelectric power from its mountains. Electric locomotives could climb steep grades better than steam. Swiss electric locomotives hauled freight through the Alps, through tunnels like the Gotthard Tunnel, opened in 1882 and 9 miles long. Japan electrified extensively after World War II. Japanese railways faced a coal shortage, so electric power made sense. The decision to electrify proved crucial for Japan's later high-speed rail success. France electrified its main lines starting in the 1950s. The SNCF, French National Railways, chose 25,000 volts AC electrification. This allowed substations to be spaced farther apart, reducing costs. Many countries adopted the French system. Railway electrification had another advantage. Electric locomotives were quieter. They produced no smoke or fumes. Cities with electrified railways had cleaner air. Tunnels didn't fill with choking smoke. Underground railways in particular benefited. The London Underground became far more pleasant when it converted from steam to electric. Steam locomotives survived longest on freight railways in developing countries. They were simple and could be repaired with basic tools. China built steam locomotives until 1999. Many were copies of Soviet designs. Chinese steam locomotives worked in coal mines and industrial railways until the 2000s. Today, only a handful of countries still use steam commercially. Zimbabwe occasionally uses steam locomotives when diesel fuel is unavailable. Heritage railways preserve steam locomotives around the world. Volunteers maintain and operate historic trains for tourists. In Britain, over 100 heritage railways operate. The Festiniog Railway in Wales has run continuously since 1865, making it the oldest independent railway company in the world. Enthusiasts spend thousands of hours restoring old locomotives. Steam locomotives that would have been scrapped now run again. Some countries never fully abandon steam. North Korea still uses steam locomotives for freight. Lack of diesel fuel and electricity means steam. Burning locally mined coal remains practical. Cuba uses old American steam locomotives from the 1920s in sugarcane fields. These locomotives were shipped to Cuba before the revolution and have been maintained for decades. Railway preservation isn't limited to locomotives. Entire stations have been preserved. St. Pancras Station in London, built in 1868, is a Gothic masterpiece. Its train shed spans 689 feet and was the largest single-span structure in the world when built. It was nearly demolished in the 1960s but was saved by preservationists. Today it serves as the London terminus for Eurostar high-speed trains. Grand Central Terminal in New York, completed in 1913, is another preserved masterpiece. Its main concourse has a ceiling painted with constellations. Over 750,000 people pass through it daily. When it opened, it was the largest railway station in the world, with 44 platforms. The terminal's construction required demolishing over 200 buildings. It sits on 2 levels, with suburban trains below and long-distance trains above. Railway stations became architectural showcases. Every major city wanted an impressive gateway. Milan Central Station, built in 1931, has a facade 656 feet wide. Its main hall is 236 feet long with a ceiling 118 feet high. The architecture mixes Art Nouveau and Art Deco with fascist monumentalism. Mussolini wanted it to represent the power of fascist Italy. Despite its troubling origins, it's now considered one of Europe's most beautiful stations. Antwerp Central Station in Belgium has been called the most beautiful railway station in the world. Completed in 1905, it combines a stone facade with a massive glass and iron train shed. The waiting room has a 246-foot-high dome. Marble staircases lead to platforms. 20 different types of marble and stone were used in its construction. When Belgium modernized the station in the 2000s, they preserved the historic building while adding modern platforms underground. Railway hotels became destinations themselves. The Canadian Pacific Railway built a series of grand hotels across Canada. The Chateau Frontenac in Quebec City, opened in 1893, looks like a French castle. The Banff Springs Hotel in Alberta, opened in 1888, was called a castle in the Rockies. These hotels were designed to attract tourists to travel on Canadian Pacific trains. The strategy worked. Railway tourism became a major industry. The transition from steam to diesel transformed railways. Diesel locomotives didn't just replace steam. They changed how railways operated. A diesel locomotive could run all day without stopping for fuel or water. It could start instantly. It didn't need a fireman. One engineer could control multiple diesel units linked together, creating enormous power when needed. General Motors dominated the American diesel locomotive market. Their EMD F-Series and E-Series locomotives became ubiquitous. Between 1939 and 1963, EMD built over 7,600 locomotives. These locomotives were modular. If an engine failed, you could replace just that unit. Maintenance became simpler. Diesel locomotives could be repaired by mechanics, not specialized craftsmen. The economics were compelling. A diesel locomotive cost more to buy than a steam locomotive, but far less to operate. Union Pacific calculated that one diesel locomotive could do the work of 3 steam locomotives while using 2/3 the crew. Maintenance costs dropped by 50%. Fuel costs were lower. Diesel fuel had more energy per gallon than coal per pound. Railways could eliminate water towers, coal yards, and ash disposal systems. American railways dieselized rapidly. The Santa Fe Railway started buying diesels in 1940. By 1959, they had retired their last steam locomotive. The Norfolk and Western Railway held out the longest among major American railways. They operated coal mines and believed in steam. They built their own modern steam locomotives as late as 1953. But even they switched to diesel by 1960. Steam's labor costs and inefficiency couldn't compete. European railways took longer to dieselize. Many European countries invested heavily in electrification instead. Britain started dieselizing in 1955 with a modernization plan. They designed multiple types of diesel locomotives and diesel multiple units. Some designs worked well, others were disasters. The first-generation British diesels had so many problems that many were scrapped after only 15 years. But lessons were learned. Later, British diesels were reliable. Germany developed powerful diesel hydraulic locomotives instead of diesel electric. A diesel hydraulic uses a hydraulic transmission instead of electric generators and motors. German engineers believed this was more efficient. Deutsche Bundesbahn built thousands of diesel hydraulic locomotives. They worked well in Germany but weren't widely adopted elsewhere. Most of the world used diesel electric. The Soviet Union developed its own diesel locomotives based on American designs. During World War II, America sent diesel locomotives to the Soviet Union under Lend-Lease. Soviet engineers studied them and created similar designs. The Soviet TE-3 diesel locomotive, introduced in 1953, was based on the American Alco design. Thousands were built and spread across the Soviet Union and Allied countries. Diesel locomotives enabled longer, heavier freight trains. In America, freight trains grew to over 100 cars regularly. Modern American freight trains often exceed 150 cars and stretch over 2 miles long. The longest freight train ever recorded ran in Australia in 2001. It was 4.6 miles long, had 682 cars, and weighed 99,734 tons. It required 8 locomotives. The train carried iron ore from a mine to a port. It ran once as a record-breaking publicity stunt. Multiple unit control was a game-changer. One engineer in the lead locomotive could control several locomotives distributed throughout a train. This distributed power prevented cars in the middle from breaking under compression or tension forces. It allowed trains to climb steep grades. American railways commonly use 4 to 6 locomotives on heavy freight trains. The locomotives communicate through cables or radio signals. Diesel locomotives revolutionized passenger service too. Streamlined diesel trains appeared in the 1930s. The Burlington Zephyr, introduced in 1934, was a sleek stainless steel train. Its diesel engine and aerodynamic design allowed it to cruise at 110 miles per hour. On May 26, 1934, it ran from Denver to Chicago, 1,015 miles, in 13 hours and 5 minutes, averaging 77 miles per hour. This was a sensation. The train drew crowds wherever it stopped. Japan imported diesel multiple units from America in the 1950s. These self-propelled passenger cars didn't need separate locomotives. Passengers sat in cars that had engines underneath. This made them efficient for routes with frequent stops. Japan improved the designs and built thousands. Diesel multiple units served rural lines across Japan. However, Japan focused on electrification for main lines. After World War II, Japan rebuilt its destroyed railways with electrification as the priority. They chose 25,000 volts AC, the same system France developed. This decision laid the groundwork for the Shinkansen. Electric power was essential for the high speeds Japan wanted to achieve. Electrification accelerated worldwide in the 1950s and 1960s. The advantages were clear for busy routes. Electric locomotives were more powerful than diesel. They could accelerate faster. They required less maintenance because they had fewer moving parts. They produced no exhaust, making them ideal for tunnels and urban areas. Most importantly, they could be much more powerful. The most powerful diesel locomotives produced about 6,000 horsepower. Electric locomotives could exceed 10,000 horsepower. France built some of the most powerful electric locomotives in the world. The SNCF BB 9200 series, introduced in 1957, produced 4,650 horsepower. Later, French electric locomotives exceeded 8,000 horsepower. These locomotives pulled heavy trains at high speeds. France's investment in electric infrastructure paid off when they developed the TGV high-speed trains in the 1970s. The Soviet Union electrified extensively. The Trans-Siberian Railway was gradually electrified from the 1930s to the 2000s. By 2002, the entire 5,672-mile route was electrified. This was a massive undertaking. Thousands of miles of overhead wires had to be strung across Siberia. Substations were built in remote locations, but it paid off. Electric locomotives could haul heavier freight trains more efficiently. The electrified Trans-Siberian became one of the world's busiest freight railways. India electrified steadily after independence. Indian railways chose 25,000 volts AC. Today, over 60% of Indian railways are electrified. India built its own electric locomotives, starting with designs licensed from Europe and later developing indigenous designs. Indian electric locomotives pull passenger trains exceeding 24 cars regularly. The electrification continues, with plans to electrify the entire broad-gauge network. China electrified rapidly starting in the 1990s. As China's economy boomed, freight traffic overwhelmed diesel locomotives. China chose electrification for new lines. Today, China has over 55,000 miles of electrified railway, more than any other country. Chinese-built electric locomotives pull freight trains over a mile long through mountain ranges. The electrification enabled China's high-speed rail expansion. Not all countries electrified. The United States has very little electrified railway outside the Northeast Corridor and some commuter lines. American freight railways chose diesel instead. The distances were too great and traffic too dispersed to justify electrification costs. Diesel fuel was cheap. Diesel locomotives were flexible, able to run anywhere. American freight railways operate the most efficient freight rail system in the world using diesel power. Australia followed a similar path. Distances are enormous and traffic relatively light. Diesel locomotives made more sense. Australian freight trains are among the longest in the world. The longest regular freight train runs in the Pilbara region, hauling iron ore. These trains routinely exceed 1.5 miles in length with over 200 cars. They use distributed power with locomotives at the front, middle, and rear. South Africa developed electric locomotives for its heavy coal and ore trains. The Blue Train, a luxury passenger service from Pretoria to Cape Town, originally used electric locomotives for part of the route. South Africa built powerful electric locomotives capable of hauling 20,000-ton trains. The Class 9E, introduced in 1978, produces over 5,000 horsepower and can haul freight trains over mountains. As diesel and electric replaced steam, passenger rail declined in some countries. In the United States, passenger rail nearly died. After World War II, Americans bought cars and flew on airplanes. Passenger trains lost money. Private railway companies slashed passenger services. Stations closed. Trains became dirty and unreliable. By 1970, passenger rail in America was in crisis. The government created Amtrak in 1971 to preserve a basic national passenger rail network. Amtrak took over passenger services from failing private railways. Amtrak struggled for decades with inadequate funding and aging equipment, but it survived. Today, Amtrak carries over 30 million passengers annually. The Northeast Corridor between Boston and Washington remains profitable, but long-distance routes require subsidies. The lack of high-speed rail puts America far behind Europe and Asia in passenger rail. Britain privatized its railways in the 1990s. The government broke up British Rail into multiple private companies. Track was separated from train operations. The privatization was controversial and messy. Some franchises failed. Accidents raised safety concerns, but passenger numbers increased dramatically. Britain now has some of the busiest railways in Europe. However, fares are among the highest in the world, and the complex system of competing operators confuses passengers. Other European countries kept their railways public. France's SNCF, Germany's Deutsche Bahn, Italy's Trenitalia, and Spain's Renfe remain state-owned, though some have private competition on certain routes. These railways invested heavily in high-speed rail and saw passenger numbers boom. Rail became competitive with cars and short-haul flights. Japan never let passenger rail decline. Japanese national railways operated at a loss after World War II, but kept investing. When they introduced the Shinkansen in 1964, it transformed their fortunes. JNR was privatized in 1987, split into regional companies. These private companies are now highly profitable. They run frequent, punctual trains on an extensive network. Japan has the highest per capita rail usage in the world. China kept railways state-owned under China Railway Corporation. In the 2000s, China began the largest railway expansion in history. They built thousands of miles of new railway, including the world's largest high-speed rail network. Chinese railways carry over 3 billion passengers annually, more than any other country. The investment was staggering, over $800 billion, but it transformed China's economy and connected the nation. High-speed rail changed everything. Before 1964, the fastest regular passenger trains ran at about 100 miles per hour. Conventional railways had limits. Tracks designed for slower trains couldn't handle higher speeds safely. Curves had to be gentle. Signaling systems couldn't react fast enough. Engineers realized that breaking the speed barrier required purpose-built railways designed specifically for high speed. Japan built the first true high-speed railway. The Tokaido Shinkansen opened on October 1, 1964, just before the Tokyo Olympics. It connected Tokyo and Osaka, 320 miles apart. Before the Shinkansen, the journey took 6 hours and 30 minutes by conventional train. The Shinkansen covered it in 4 hours at speeds up to 130 miles per hour. Today, the same journey takes 2 hours and 30 minutes at speeds up to 177 miles per hour. The Shinkansen was revolutionary. It used entirely new tracks with no level crossings. Every crossing was a bridge or tunnel. The tracks were built to minimize curves. Where curves existed, the track was banked to allow high speeds. The trains were electric multiple units, not locomotives pulling coaches. Every car had motors underneath. This distributed power allowed faster acceleration. The trains used continuous cab signaling. Information about track conditions and speed limits was transmitted directly to the driver's cab. If the driver didn't respond to a speed restriction, the automatic train control system would slow the train automatically. This safety system was years ahead of anything else in the world. It worked. In over 60 years of operation, the Shinkansen has never had a fatal accident caused by train collision or derailment. The Shinkansen was designed with earthquake protection. Japan experiences thousands of earthquakes annually. Sensors detect earthquake waves. When a major earthquake is detected, the system automatically stops all trains. In the 2011 earthquake that triggered the tsunami, 27 Shinkansen trains were operating. All received automatic stop signals within seconds of the first earthquake waves. Not a single passenger was injured on any Shinkansen train, though some derailed at slow speeds. The original Shinkansen trains, called Series 0, had a distinctive bullet nose. This design reduced air resistance and gave the Shinkansen its English nickname, the Bullet Train. The trains had 16 cars and carried over 1,300 passengers. They were comfortable with large seats and smooth rides. The success was immediate. The Shinkansen made a profit within 7 years, far sooner than projected. Japan expanded the Shinkansen network. The Sanyo Shinkansen extended service to Hiroshima and Fukuoka in 1975. The Tohoku Shinkansen reached northern Japan in 1982. The Joetsu Shinkansen connected Tokyo to Niigata on the west coast. Today, Japan has over 1,700 miles of Shinkansen lines. They carry over 350 million passengers annually. During peak hours, trains depart Tokyo for Osaka every 10 minutes. The Shinkansen inspired the world. France started planning its own high-speed railway in the 1960s. The TGV, Train à Grande Vitesse, meaning high-speed train, opened between Paris and Lyon in 1981. The TGV used similar principles to the Shinkansen but pushed speeds higher. The original TGV reached 168 miles per hour in regular service. The 264-mile journey from Paris to Lyon took 2 hours. French engineers designed the TGV differently from the Shinkansen. TGV trains have locomotives at each end and unpowered passenger cars between them. This was cheaper than putting motors under every car. The TGV also ran on dedicated high-speed lines only for sections where traffic was heaviest. Between cities, it used upgraded conventional tracks. This reduced construction costs while still achieving high speeds. The TGV proved even faster than the Shinkansen. In 1981, a TGV set a world record of 236 miles per hour. In 1990, another TGV reached 320 miles per hour. In 2007, a specially modified TGV reached 357 miles per hour, a record for conventional rail that still stands. These speed records weren't just stunts. They proved the technology and generated publicity. France built TGV lines across the country. The TGV Sud-Est to Lyon was followed by the TGV Atlantique to western France, the TGV Nord to northern France and Belgium, and the TGV Méditerranée to the south. International TGV lines connected France to Switzerland, Italy, Spain, and Germany. The Channel Tunnel, opened in 1994, allowed Eurostar trains based on TGV technology to run from Paris and Brussels to London. France now has over 1,100 miles of high-speed lines. Over 100 million passengers ride the TGV annually. Germany developed its own high-speed trains, the Intercity Express, or ICE. The first ICE line opened in 1991 between Hamburg and Munich. German ICE trains reached 200 miles per hour on new high-speed lines. Unlike France's approach, Germany upgraded many existing lines instead of building entirely new routes. This saved money but limited speeds in some areas. German engineering made the ICE trains incredibly smooth and quiet. The ride quality is exceptional even at high speeds. Germany built several purpose-built high-speed lines. The line from Cologne to Frankfurt, opened in 2002, runs through mountainous terrain. Engineers built tunnels and viaducts to maintain high speeds. The longest tunnel is nearly 6 miles. The line cut travel time from 2 hours 15 minutes to 1 hour. Germany now has over 900 miles of high-speed railway operating at 155 miles per hour or faster. Spain built Europe's longest high-speed network. The AVE, Alta Velocidad Española, opened in 1992 between Madrid and Seville. Spain chose the same track gauge as France, allowing international services. Spain invested heavily, building over 2,400 miles of high-speed railway. AVE trains reach 193 miles per hour. Madrid now has high-speed connections to Barcelona, Valencia, Malaga, and other cities. Spain's high-speed network is second only to China's in total length. Italy's high-speed network connects Milan, Bologna, Florence, Rome, and Naples. The Frecciarossa, or Red Arrow, trains reach 186 miles per hour. The Rome to Milan journey takes 3 hours for 370 miles. Private company Italo competes with state-owned Trenitalia on the same routes. This competition drove down fares and increased service frequency. Italy's high-speed railway is one of the few in the world with genuine competition between operators. China entered high-speed rail late but grew faster than anyone. China's first high-speed railway opened in 2007. By 2025, China has over 28,000 miles of high-speed railway, more than the rest of the world combined. China Railway High Speed, abbreviated CRH, trains connect every major city. The busiest routes have trains every few minutes. Over 2 billion passengers ride Chinese high-speed trains annually. Chinese high-speed trains reach 217 miles per hour in regular service. China imported technology from Japan, Germany, France, and Canada, then developed its own designs. The Fuxing train, introduced in 2017, is entirely Chinese designed. It operates at 217 miles per hour and has been tested at 250 miles per hour. China now exports high-speed train technology to other countries. The Beijing to Shanghai high-speed railway, opened in 2011, is 819 miles long. The journey takes 4 hours and 18 minutes, averaging 190 miles per hour. Before high-speed rail, the same journey took 10 to 12 hours by conventional train. The high-speed railway carries over 100 million passengers annually. At peak times, trains depart every 5 minutes. The railway made a profit within 4 years, despite costing $33 billion to build. China built high-speed railways in extremely challenging terrain. The Lanzhou to Urumqi line crosses deserts where summer temperatures exceed 104 degrees Fahrenheit. The trackbed had to be specially designed to handle thermal expansion. The Guiyang to Guangzhou line crosses mountainous terrain with 238 tunnels and 510 bridges. Over 80% of the line is on bridges or in tunnels. The Sichuan to Tibet Railway, under construction, will be the highest railway in the world, reaching elevations over 13,000 feet. Taiwan built its own high-speed railway in 2007. The Taiwan High-Speed Rail runs 200 miles from Taipei to Kaohsiung. It uses Japanese Shinkansen technology. Trains reach 186 miles per hour. The journey takes 1 hour and 45 minutes, compared to 4 hours by conventional train. The railway carries over 60 million passengers annually. South Korea opened its KTX high-speed railway in 2004. KTX uses French TGV technology. The main line connects Seoul to Busan, 255 miles. Trains reach 190 miles per hour. The journey takes 2 hours and 30 minutes. Before KTX, the same journey took over 4 hours. South Korea expanded its high-speed network to other cities. KTX carries over 60 million passengers annually. Turkey opened high-speed rail between Ankara and Istanbul in 2014. The 357-mile journey takes 3 hours and 30 minutes at speeds up to 155 miles per hour. Turkey is expanding its high-speed network to connect other cities. Saudi Arabia opened a high-speed railway between Mecca and Medina in 2018. It uses Spanish train technology and reaches 186 miles per hour. Morocco opened Africa's first high-speed railway in 2018. The line connects Casablanca and Tangier, 200 miles. Trains reach 200 miles per hour using French TGV technology. The journey takes 2 hours and 10 minutes. Before high-speed rail, the same journey took 4 hours and 45 minutes. Morocco plans to extend the line to Marrakesh. India is building its first high-speed railway between Mumbai and Ahmedabad. The 320-mile line will use Japanese Shinkansen technology. Trains will reach 200 miles per hour. The journey will take 2 hours compared to 7 hours by conventional train. Construction has been slow due to land acquisition issues. India also plans high-speed railways connecting other major cities. Indonesia opened Southeast Asia's first high-speed railway in CE 2023. The line connects Jakarta and Bandung, 88 miles. Chinese-built trains reach 217 miles per hour. The journey takes 40 minutes compared to 3 hours by road. This is part of a planned high-speed railway to Surabaya, over 400 miles away. The United States lags far behind in high-speed rail. The Acela Express runs on the Northeast Corridor between Boston and Washington. It reaches 150 miles per hour on some sections, making it the fastest train in America. But the average speed is much lower because the track is old and shared with slower trains. The journey from New York to Washington takes 2 hours and 45 minutes for 225 miles, averaging 82 miles per hour. California is building a high-speed railway between San Francisco and Los Angeles. Construction began in 2015 but has been plagued by delays and cost overruns. The original budget was $33 billion. Current estimates exceed $100 billion. The project is controversial. Only a small section in the Central Valley is under construction. When complete, trains will reach 220 miles per hour and cover the 380 miles in 2 hours and 40 minutes. High-speed rail faces challenges in America. Land is expensive. Environmental reviews take years. Political opposition delays projects. Americans prefer cars and planes. But rising air travel costs and highway congestion are making high-speed rail more attractive. Texas is planning a high-speed railway between Dallas and Houston using Japanese technology. Florida's Brightline connects Miami to Orlando with trains reaching 125 miles per hour, with plans to increase speeds. Freight trains are the workhorses of global commerce. While passenger trains get attention for speed and luxury, freight trains quietly move the economy. In the United States alone, freight trains move over 1.6 billion tons of cargo annually. That's roughly 40% of all freight moved in America. No other country relies on freight rail as heavily as the United States. American freight railways are the most efficient in the world. They move 1 ton of freight 470 miles on a single gallon of fuel. Trucks manage only 150 miles per gallon per ton. This efficiency comes from low rolling resistance. Steel wheels on steel rails create far less friction than rubber tires on asphalt. A single freight train can carry as much as 300 trucks. This reduces highway congestion and pollution. American freight trains are enormous. A typical freight train has 100 to 150 cars and stretches over a mile long. The longest trains exceed 200 cars and are nearly 3 miles long. These trains weigh 15,000 to 20,000 tons when fully loaded. They require multiple locomotives, often 4 to 6 units, generating a combined 24,000 horsepower or more. The locomotives are distributed throughout the train to manage forces on the couplers. Running such long trains requires sophisticated technology. Distributed power systems allow the engineer in the lead locomotive to control locomotives in the middle and rear of the train. Radio signals or cables transmit commands. The remote locomotives respond in synchronization with the lead unit. This prevents the train from breaking apart under the compression and tension forces that occur when accelerating, braking, or climbing grades. Modern freight locomotives are marvels of engineering. The GE ES44AC, one of the most common locomotives in North America, produces 4,400 horsepower from a 16-cylinder diesel engine. The engine drives an alternator that generates electricity. Electric motors on the axles turn the wheels. This diesel-electric system is more efficient than a mechanical transmission for heavy loads. The locomotive weighs 432,000 pounds. All that weight provides traction. Without it, the wheels would just spin. Freight trains carry every imaginable cargo. Coal trains are among the heaviest. A unit train carrying nothing but coal from a mine to a power plant can have 130 cars. Each car carries 120 tons of coal. The entire train weighs over 18,000 tons loaded. These trains run in a continuous loop, loading at the mine, delivering to the power plant, and returning empty. Some coal trains run multiple times per day on the same route. Intermodal trains carry shipping containers and truck trailers. These trains revolutionized freight transport. A container can be loaded at a factory, shipped by train to a port, loaded onto a ship, transported across the ocean, unloaded at another port, shipped by train to a distribution center, and loaded onto a truck for final delivery. The contents are never touched. This intermodal system reduced shipping costs dramatically. The first intermodal service started in 1956 when Malcolm McLean put 58 truck trailers on a ship without unloading them. The idea spread to railways. By the 1980s, double-stack container trains appeared. These trains carry containers stacked too high on special well cars. The containers sit in a recessed well, allowing them to stack without exceeding height clearances under bridges and tunnels. A double-stack train can carry as much cargo as 280 trucks. Grain trains carry wheat, corn, and other agricultural products. These trains use covered hopper cars that load from the top and unload from the bottom. A unit grain train of 100 cars can carry 10,000 tons of grain. America exports enormous quantities of grain. Trains carry it from farms in the Midwest to ports on the Gulf Coast or the Pacific Northwest, where it's loaded onto ships bound for Asia, Africa, and South America. Oil trains became common after the fracking boom in the 2000s. These trains carry crude oil from production sites to refineries. Each tank car holds 30,000 gallons. A 100-car oil train carries 3 million gallons of crude oil. These trains sparked controversy after several accidents. In 2013, an oil train derailed in Lac-Mégantic, Quebec. The resulting fire killed 47 people and destroyed half the town. Railways and governments implemented stricter safety regulations for oil trains. Ore trains carry iron ore, copper ore, and other minerals from mines to processing facilities. These are some of the heaviest trains in the world. In Australia, iron ore trains in the Pilbara region routinely exceed 2.5 miles in length and weigh over 40,000 tons. The trains use up to 8 locomotives. They run on dedicated railways built specifically for hauling ore from mines to ports. BHP operates trains that are over 3 miles long with 330 cars. The longest and heaviest trains in the world run in Australia and Brazil. In 2001, BHP Billiton ran a train in Western Australia that was 4.6 miles long with 682 cars. The train weighed 99,734 tons and required 8 locomotives. It was a publicity stunt to break the world record, but similar trains run regularly on shorter routes. These ORI trains operate on private railways owned by mining companies. Brazil's ore trains are similarly massive. Vale, the mining company, operates trains carrying iron ore from inland mines to coastal ports. These trains have up to 330 cars and weigh 40,000 tons loaded. Brazil's Carajás Railway, 550 miles long, was built specifically to transport iron ore. It carries over 100 million tons of iron ore annually, making it one of the busiest freight railways in the world by tonnage. Russia relies heavily on freight rail. The Trans-Siberian Railway and other Russian railways carry over 1.3 billion tons of cargo annually. Russian freight trains are shorter than American trains, but run more frequently. The trains carry coal, oil, metals, timber, and manufactured goods across the vast distances of Russia. Without these railways, Siberia would be economically isolated. China moves more freight by rail than any other country except the United States. Chinese railways carry over 3 billion tons of cargo annually. Coal is the largest single commodity, accounting for over half of all freight. Trains carry coal from mines in Shanxi and Inner Mongolia to power plants across China. Container trains carry manufactured goods from factories to ports for export. China is expanding freight rail capacity to reduce truck traffic on highways. India's railways carry over 1.2 billion tons of freight annually. Coal, iron ore, cement, and grain are the main commodities. Indian freight trains are heavy, often exceeding 5,000 tons. They run on the same tracks as passenger trains, which complicates scheduling. Freight trains must yield to passenger trains, causing delays. India is building dedicated freight corridors to separate freight and passenger traffic. These new railways will allow longer, faster freight trains. Europe moves less freight by rail than other continents. European freight railways carry about 400 million tons annually, far less than America, despite similar economic size. European railways prioritize passenger traffic. Freight trains must compete for track space with frequent passenger trains. This limits freight train length and frequency. European freight trains are typically 50 to 80 cars, much shorter than American trains. However, Europe is trying to increase freight rail usage to reduce truck traffic and pollution. The European Union has funded construction of freight corridors across borders. The challenge is that each country has different signaling systems, operating rules, and sometimes different voltages for electric locomotives. A freight train crossing multiple countries needs multiple signal systems and may need to change locomotives at borders. The Channel Tunnel carries significant freight traffic between Britain and continental Europe. Freight trains run through the tunnel carrying containers, trucks on special wagons, and bulk cargo. The tunnel operates 24 hours a day. At peak times, a freight train runs through every 10 minutes. The tunnel reduced shipping time between Britain and Europe from days by sea to hours by rail. Freight railways operate very differently from passenger railways. Freight trains run on flexible schedules based on demand. A freight train might be assembled from cars going to multiple destinations. At classification yards, trains are broken apart and reassembled. Cars are sorted by destination. This process, called switching, uses small locomotives called switchers to move individual cars or small groups of cars around the yard. The largest classification yards are vast facilities covering several square miles. Bailey Yard in North Platte, Nebraska is the largest in the world. It covers 2,850 acres and handles 14,000 rail cars daily. The yard has a hump where cars are pushed over a small hill. Gravity pulls them down the other side into different tracks based on their destination. Computer-controlled switches route each car to the correct track. Retarders slow the cars to prevent collisions. Modern freight railways use sophisticated logistics systems. Computers track every rail car in real time using GPS and RFID tags. Customers can see exactly where their shipment is at any moment. Dispatch centers monitor all trains on the network. Dispatchers control signals and switches, routing trains efficiently. If a train breaks down or encounters a problem, dispatchers reroute other trains to minimize delays. Freight train crews consist of an engineer who operates the train and a conductor who manages paperwork and operations. In the past, freight trains had brakemen who walked along the train setting handbrakes. Modern air brakes eliminated this dangerous job. Some railways are testing single-person crews with just an engineer and no conductor. This is controversial. Unions argue conductors are essential for safety. Railways argue modern technology makes them unnecessary. Freight trains carry hazardous materials that require special handling. Tank cars carry chemicals, petroleum products, and liquefied gases. These cars must meet strict safety standards. They have thick steel walls, pressure relief valves, and protective shields. Trains carrying hazardous materials are subject to speed restrictions and routing requirements. They must avoid populated areas when possible. Railway safety has improved dramatically. The accident rate on American freight railways has decreased by 80% since 1980. Improved track maintenance, better brakes, and advanced signaling systems all contributed. Positive Train Control, or PTC, is a system that automatically stops trains before collisions or derailments occur. It uses GPS, wireless networks, and onboard computers. By law, all major American railways must have PTC installed. The system costs billions but prevents accidents. Track maintenance is crucial for freight railways. Heavy trains wear out tracks quickly. Rails develop defects from repeated stress. Freight railways inspect tracks constantly using specialized cars with ultrasonic sensors and lasers. These cars can detect internal cracks and geometry problems invisible to the eye. Maintenance crews replace worn rails and ties, tamp ballast, and grind rails to maintain the correct profile. Modern freight railways use continuous welded rail instead of jointed rail. Traditional rails were 39 feet long, bolted together. The joints created a rhythmic clicking sound as wheels passed over them. Continuous welded rail has no joints for up to 1,500 feet. Rails are welded together into long ribbons. This creates a smoother ride and reduces maintenance. The rails must be installed at a neutral temperature so they don't buckle when hot or pull apart when cold. Urban rail systems transformed cities. The first underground railway opened in London in 1863. The Metropolitan Railway ran from Paddington to Farringdon Street, just 4 miles. It used steam locomotives in tunnels, creating thick smoke and choking fumes. Despite the discomfort, it was an immediate success. 30,000 people rode it on the first day. Within a year, it carried 9.5 million passengers. The smoke problem in underground railways was severe. Passengers arrived at their destinations covered in soot. Locomotive crews suffered respiratory problems. Engineers designed special condensing steam locomotives that stored exhaust steam in tanks instead of releasing it. This reduced smoke but didn't eliminate it. The real solution came with electrification. The City and South London Railway, opened in 1890, was the first electric underground railway. The London Underground expanded rapidly. By 1900, London had several underground lines. Deep-level tunnels were bored through the clay beneath the city. These tunnels were too deep for steam locomotives. Electric trains were essential. The familiar roundel symbol and mind the gap warnings became iconic. Today, the London Underground has 250 miles of track, 272 stations, and carries 1.3 billion passengers annually. The Paris Metro opened in 1900, just in time for the World's Fair. It grew rapidly, with Art Nouveau station entrances designed by Hector Guimard becoming symbols of Paris. The Paris Metro is dense, with stations close together. In central Paris, you're never more than 500 meters from a metro station. The system has 133 miles of track and 308 stations. Over 1.5 billion passengers ride it annually, making it one of the busiest metro systems in the world. New York opened its first subway in 1904. The Interborough Rapid Transit Company built a line from City Hall to 145th Street in Manhattan. Over 100,000 people rode it on opening day. New York's subway expanded to become the largest in America. It has 248 miles of passenger routes and 472 stations. The system runs 24 hours a day, 365 days a year, unlike most metro systems that close at night. Over 1.7 billion passengers ride it annually. The New York subway is famous for its complexity. Express and local trains share the same routes. 4 tracks allow express trains to skip stations while local trains stop at all stations. This system is efficient but confusing for visitors. The subway serves all 5 boroughs of New York City. It's essential to the city's functioning. Without it, Manhattan's streets couldn't handle the traffic. Tokyo's metro system is the busiest in the world. 2 separate networks operate: Tokyo Metro with 9 lines and Toei Subway with 4 lines. Together, they carry over 3.1 billion passengers annually. During rush hour, trains arrive every 2 to 3 minutes. Station platforms are packed with commuters. Staff called pushers literally push passengers into crowded trains so the doors can close. Some lines have women-only cars to prevent harassment during crowded rush hours. Moscow Metro opened in 1935 under Stalin. It was built as a showcase of Soviet achievement. The stations are palaces. Ornate chandeliers hang from ceilings. Marble columns line platforms. Mosaics and statues depict Soviet heroes and workers. Each station has a unique design. Komsomolskaya Station has Baroque-style ceilings. Mayakovskaya Station has Art Deco mosaics. The Moscow Metro is one of the deepest metros in the world. Some stations are over 200 feet underground, deep enough to serve as bomb shelters. The Moscow Metro carries over 2.5 billion passengers annually. It's famous for efficiency and cleanliness. Trains run every 90 seconds during rush hour. The system has 15 lines and over 200 stations. Despite its beauty, the Moscow Metro was built with brutal methods. Forced labor from Gulag prisoners did much of the construction. Thousands died building it. This dark history is rarely acknowledged in Russia. Shanghai Metro is the longest metro system in the world by route length. It has over 500 miles of track, more than London and New York combined. The system opened in 1993 with just one line. Explosive growth came after 2000 as Shanghai modernized. New lines opened every few years. Today, Shanghai Metro has 20 lines and over 500 stations. It carries over 4 billion passengers annually, more than any other metro system. Beijing Subway is the second longest metro with over 470 miles of track. It has 27 lines and over 450 stations. The system carries over 3.8 billion passengers annually. Beijing Metro expanded rapidly for the 2008 Olympics. New lines continue to open regularly. The system is modern with platform screen doors, air conditioning, and real-time information displays. During rush hour, trains are packed to capacity. Seoul Metropolitan Subway is one of the most extensive metro systems in the world. It has over 200 miles of track in Seoul proper with additional suburban lines. The system is famous for cleanliness and technology. Stations have shops, restaurants, and underground shopping malls. Free Wi-Fi is available throughout the system. Trains have heated seats in winter. Over 2.5 billion passengers ride Seoul Metro annually. Mexico City Metro is the busiest metro in North America. It carries over 1.6 billion passengers annually. The system has 12 lines and over 195 stations. Fares are extremely cheap, making it accessible to everyone. The metro uses symbols instead of just names for stations. This helps illiterate passengers navigate the system. Each station has a unique pictogram displayed on platforms and trains. Cairo Metro is the first metro system in Africa. The first line opened in 1987. Today, Cairo Metro has 3 lines and 70 stations. It carries over 1 billion passengers annually. The metro provides relief from Cairo's notorious traffic congestion. The first 2 cars of every train are reserved for women only. This policy addresses harassment concerns and provides a more comfortable experience for female passengers. Light rail is different from heavy metro systems. Light rail trains run on street level, often sharing roads with cars. They're lighter, smaller, and cheaper to build than full metros. Light rail experienced a renaissance starting in the 1980s. Cities that had torn up old streetcar lines began building modern light rail systems. San Diego opened one of the first modern light rail systems in America in 1981. The San Diego Trolley uses both dedicated tracks and street running sections. It connects downtown San Diego with suburbs and the Mexican border. The system was built cheaply by using abandoned freight railway corridors. It proved light rail could be cost-effective. Other American cities followed. Portland opened its Max Light Rail in 1986. Portland became known for transit-oriented development. The city built the light rail first, then encouraged dense housing and businesses near stations. This created walkable neighborhoods where people could live without cars. The strategy worked. Portland's light rail carries over 100,000 passengers daily. European cities never completely abandoned trams and streetcars like American cities did. Many European cities maintained and modernized their systems. Amsterdam has an extensive tram network. Melbourne, Australia, has the largest tram network in the world with over 150 miles of track. Modern trams are sleek, quiet, and environmentally friendly. Modern trams are far more advanced than old streetcars. They have air conditioning, low floors for easy boarding, and regenerative braking that feeds electricity back into the grid. Some trams are wireless, using batteries or supercapacitors instead of overhead wires. This eliminates the visual clutter of wires in historic city centers. Bordeaux, France, pioneered this with ground-level power supply systems. Monorails are railways with trains running on a single rail, usually elevated. The Seattle Monorail, built for the 1962 World's Fair, still operates. Japan has several monorail systems. The Tokyo Monorail connects the city to Haneda Airport, carrying over 300,000 passengers daily. The Chongqing Rail Transit in China has the busiest monorail line in the world, carrying over 900,000 passengers daily on Line 3. Monorails have advantages. They take up less space than conventional railways. Elevated monorails don't interfere with street traffic. They're quiet and provide good views, but they have disadvantages too. They're expensive to build. Trains can't switch between lines easily. If a train breaks down, the entire line shuts down. This is why most cities prefer conventional metro systems. Mountain railways use special technologies to climb steep slopes. Rack railways have a toothed rail between the running rails. Trains have cog wheels that mesh with the toothed rack, pulling the train up slopes too steep for normal adhesion. The Mount Washington Cog Railway in New Hampshire, opened in 1869, was the first rack railway in the world. It climbs to the summit at 6,188 feet with grades up to 37%. The Pilatus Railway in Switzerland has the steepest rack railway in the world with gradients up to 48%. That's almost 1 foot of rise for every 2 feet of horizontal distance. The train crawls up the mountain at 2.5 miles per hour. The view from the top is spectacular. The technology works perfectly. The railway has operated since 1889 with no serious accidents. Funiculars are cable railways on steep slopes. A cable pulls one car up while another descends. The two cars are connected by the cable passing over a pulley at the top. The weight of the descending car helps pull the ascending car up, making the system energy efficient. Funiculars operate in cities with steep hills. San Francisco has cable cars, though technically they're not funiculars because the cable runs continuously under the street. The Linton and Lynmouth Cliff Railway in England is water-powered. The car at the top fills a tank with water, making it heavy. The car at the bottom empties its tank. Gravity pulls the heavy car down, lifting the light car up. At the bottom, the water tank empties. At the top, it refills. No electricity is needed. This ingenious system has operated since 1890. Maglev trains use magnetic levitation instead of wheels. Magnets lift the train above the track, eliminating friction. This allows extremely high speeds with a smooth, quiet ride. The first commercial maglev opened in Birmingham, England in 1984. It connected the airport to the railway station. It operated for 11 years before closing due to reliability problems with the technology. Japan developed maglev technology extensively. The Linamo in Nagoya is a low-speed maglev used for urban transit. It operates reliably and quietly. Japan is building the Chuo Shinkansen, a high-speed maglev between Tokyo and Osaka. The line will run mostly in tunnels through mountains. Trains will reach 314 miles per hour, cutting the journey time from 2 hours 30 minutes to 1 hour 7 minutes. The project is expensive and technically challenging, with completion expected around 2037. China opened the world's first high-speed commercial maglev in 2004 in Shanghai. The Shanghai Maglev connects Pudong Airport to the city, covering 19 miles in 7 minutes. Trains reach 268 miles per hour, making it the fastest commercial train service in the world. The ride is smooth and almost silent. However, the technology is expensive. China hasn't built additional maglev lines, choosing conventional high-speed rail instead. South Korea opened a low-speed maglev at Incheon Airport in 2016. The train connects terminals at the airport. It operates at 68 miles per hour. The system is fully automated with no drivers. South Korea is developing higher-speed maglev technology with trains capable of 373 miles per hour tested. Commercial deployment hasn't happened yet. Automated metros operate without drivers. Computers control the trains completely. The first fully automated metro opened in Lille, France in 1983. Today, over 60 cities have automated metro systems. They're safer than human-driven trains because computers don't make mistakes or get distracted. They can run more frequently because they don't need driver brakes. They're more efficient, accelerating and braking optimally to save energy. Copenhagen Metro is fully automated. It opened in 2002 and operates 24 hours a day. Trains run every 2 to 6 minutes depending on time of day. There are no drivers, conductors, or ticket collectors. Everything is automated. The system is reliable with over 98% on-time performance. Passengers trust it completely. Dubai Metro, opened in 2009, is the longest automated metro in the world. It has 47 miles of track, all elevated or underground with no street-level sections. Trains are driverless and run every few minutes. The metro transformed Dubai, providing efficient public transportation in a city dominated by cars. Over 200 million passengers ride it annually. Vancouver's SkyTrain has been automated since it opened in 1985. The system works flawlessly. Trains run frequently and punctually. The automated system proved so reliable that Vancouver expanded it multiple times. Today, SkyTrain has over 50 miles of track and carries over 150 million passengers annually. The system operates in all weather conditions, including snow and ice. Railways are one of the most environmentally friendly forms of transportation. A freight train can move 1 ton of cargo 470 miles on a single gallon of fuel. Trucks achieve only 150 miles per gallon per ton. This makes rail 4 times more fuel efficient than trucking. For passengers, trains emit 66% less carbon dioxide per passenger mile than cars and 73% less than airplanes. Electric trains are even cleaner. They produce no direct emissions. If the electricity comes from renewable sources like wind, solar, or hydroelectric, the train is essentially carbon neutral. Countries with extensive electric rail networks have significantly lower transportation emissions than countries dependent on cars and trucks. Shifting freight from trucks to trains reduces highway congestion. 1 freight train replaces 300 trucks. This means fewer vehicles on highways, less wear on roads, fewer accidents, and shorter travel times for cars. Studies show that every $1 billion invested in freight rail infrastructure takes 3 million trucks off highways annually. Noise pollution is lower with trains than trucks. A freight train passing creates about 90 decibels of noise. A truck creates 95 decibels. That might seem like a small difference, but decibels are logarithmic. 5 decibels is actually a significant difference. High-speed trains are even quieter. Modern high-speed trains at 200 miles per hour create less noise than highways at peak traffic. Railways use less land than highways. A double-track railway can carry more passengers and freight than a 10-lane highway while using 1/5 the land. In densely populated areas, this is crucial. Urban railways run underground or elevated, using almost no ground-level space. Highways cut through neighborhoods, dividing communities. Railways can unite them, especially when built underground. Safety statistics favor trains over cars. Traveling by train is 17 times safer than traveling by car per mile. Rail accidents are rare and becoming rarer. Modern safety systems like positive train control prevent most accidents before they happen. Japan's Shinkansen has carried over 10 billion passengers in 60 years without a single passenger fatality from collision or derailment. The future of rail involves several emerging technologies. Hydrogen trains are being developed and tested. They use hydrogen fuel cells to generate electricity, powering electric motors. The only emission is water vapor. Germany introduced the world's first hydrogen-powered passenger trains in 2018. The Coradia Island trains run on regional routes. They're quiet, produce no pollution, and can travel up to 600 miles on a single tank of hydrogen. Battery electric trains are another alternative. These trains carry large batteries instead of diesel engines. They can run on non-electrified tracks, charging from overhead wires on electrified sections. This allows railways to reduce infrastructure costs. They don't need to electrify every mile of track. Battery trains can coast through gaps. Japan, Europe, and North America are testing battery electric trains. Autonomous trains are advancing beyond metro systems. Freight railways are testing fully autonomous freight trains. Rio Tinto operates autonomous ore trains in Australia. These trains run without crews, controlled by computers in a central operations center. Cameras and sensors monitor the tracks. The system works reliably. Rio Tinto has operated autonomous trains since 2018 without serious incidents. Some experts believe fully autonomous freight trains will be common by 2035. The technology exists. Regulatory and labor issues are the main obstacles. Unions oppose eliminating train crews. Regulators worry about safety without humans on board. But the economic and efficiency benefits are substantial. Autonomous trains can run 24 hours without crew rest requirements. They accelerate and brake optimally, saving fuel. High-speed rail continues expanding globally. India is building multiple high-speed lines. Thailand is planning a high-speed railway to China. Malaysia and Singapore plan to connect their cities with high-speed rail. Even the United States, long resistant to high-speed rail, has projects under construction or in planning stages in California, Texas, and the Northeast. The next generation of high-speed trains will be even faster. China tested a maglev train at 373 miles per hour in 2021. Japan is building a maglev line with trains operating at 314 miles per hour. These speeds rival airplanes for journeys under 600 miles when you account for airport security and boarding time. A 300-mile journey by train at 300 miles per hour takes 1 hour. The same journey by plane takes at least 2 hours, including airport time. Hyperloop technology promises even higher speeds. Hyperloop would use pods traveling through near-vacuum tubes at up to 700 miles per hour. Magnetic levitation would eliminate friction. Low air pressure would eliminate air resistance. Several companies are developing Hyperloop technology. Test tracks have been built. Pods have been tested at over 200 miles per hour, but no commercial Hyperloop exists yet. Critics question whether Hyperloop is practical. Building hundreds of miles of vacuum tubes is expensive. Any leak would compromise the system. Emergency evacuation from a tube would be difficult. Curves and elevation changes must be gradual at such high speeds, requiring expensive tunneling or elevated structures. Traditional high-speed rail is proven technology. Hyperloop remains experimental. Urban air mobility is another concept being explored. Electric vertical takeoff and landing aircraft, or eVTOLs, could transport passengers between city centers and airports. These would complement trains rather than replace them. Trains will always be more efficient for moving large numbers of people, but eVTOLs could serve niche markets where trains can't reach. Railway digitalization is transforming operations. Digital twins create virtual models of entire railway networks. Engineers can simulate changes before implementing them. Predictive maintenance uses sensors and AI to predict component failures before they happen. This prevents breakdowns and reduces maintenance costs. Trains report their condition in real time. If a bearing is overheating or a brake is wearing thin, maintenance crews know before it fails. Smart ticketing eliminates paper tickets. Passengers use smartphones or contactless cards. They tap on and off. The system calculates the fare automatically. This speeds boarding and reduces fraud. Transport for London pioneered this with Oyster cards and now accepts contactless credit cards. Other cities are following. In the future, passengers might not need tickets at all. Facial recognition or smartphone tracking could charge fares automatically. Real-time passenger information has become standard. Apps show exactly where trains are and when they'll arrive. Delays are communicated instantly. Passengers can plan better. Crowding information tells passengers which train cars have space. This distributes passengers evenly, making journeys more comfortable and boarding faster. Railway renaissance is happening in unexpected places. Los Angeles, once the car capital of the world, is building one of the largest metro expansions in America. The city will add over 50 miles of new metro and light rail lines by 2028, funded by local sales tax increases that voters approved. Car-dependent LA is becoming a transit city. Africa is investing in railways after decades of neglect. Ethiopia opened a new railway to Djibouti in 2016, replacing a defunct colonial line. Kenya opened a railway from Mombasa to Nairobi in 2017. Nigeria is upgrading railways between major cities. These projects are often funded and built by China as part of the Belt and Road Initiative. They're transforming African logistics and economic development. South America is rediscovering railways. Brazil is planning high-speed rail between Rio de Janeiro and São Paulo. Argentina is upgrading its long-neglected railway network. Chile is improving urban rail in Santiago. These countries abandoned railways in the late 20th century, focusing on highways. They're reversing course as traffic congestion becomes unbearable. The COVID-19 pandemic temporarily devastated passenger rail. Ridership dropped 80 to 90%. Railways lost billions, but recovery has been strong. People are returning to trains. Many people discovered they prefer trains to cars for commuting. Cities that maintained service during the pandemic saw faster recovery. Railways that cut service struggled to win passengers back. Remote work changed commuting patterns. Peak hour congestion decreased. Midday and weekend travel increased. Railways are adapting. Flexible fare structures reward off-peak travel. Service patterns are shifting. Some railways run trains every 15 minutes all day instead of crowding service into rush hours. This provides better service and distributes passenger loads more evenly. Climate change is making railways more attractive. Governments worldwide are setting carbon reduction targets. Transportation produces about 25% of global carbon emissions. Shifting people and freight to railways is one of the most effective ways to reduce emissions. Every person who switches from car to train reduces their carbon footprint by 80%. Extreme weather affects railways. Floods wash out tracks. Heat waves buckle rails. Wildfires close routes. Railways are adapting. Engineers are designing infrastructure to withstand higher temperatures and heavier rainfall. Drainage systems are being upgraded. Track is being modified to handle greater thermal expansion. Bridges and tunnels are being reinforced against floods. Railways are being integrated with other transportation modes. Transit-oriented development builds housing, offices, and shops around railway stations. People can walk or bike to stations instead of driving. This reduces car dependency. Cities like Tokyo, Hong Kong, and Copenhagen show this works. People live car-free lives because railways, buses, bikes, and walking meet all their needs. Bike share and scooter share systems complement railways. Passengers use bikes or scooters for the first and last mile of their journey. Many railway stations have bike parking and bike share docking stations. In the Netherlands, nearly half of railway passengers arrive by bicycle. In China, bike share apps are integrated with railway ticketing apps. Ride-hailing services like Uber and Lyft can complement railways too. Instead of driving the entire journey, people take ride-hailing to the station, ride the train for the long distance, and take another ride-hailing from the destination station. This is cheaper and faster than driving the entire way, especially in congested areas. The economics of railways are improving. Construction costs are decreasing in some countries. China builds high-speed railways for about $20 million per mile. Europe and America spend $50 to $100 million per mile for the same thing. The difference is labor costs, regulations, and construction methods. Some countries are learning from China to reduce costs without sacrificing quality. Private investment in railways is increasing. Infrastructure funds see railways as stable, long-term investments. Freight railways generate steady cash flows. Passenger railways on busy routes are profitable. Governments are encouraging private participation through public-private partnerships. Private companies design, build, and sometimes operate railways while governments provide land and some funding. Railway jobs are evolving. Automation eliminates some jobs but creates others. Fewer engineers and conductors are needed, but more software engineers, data analysts, and AI specialists are needed. Railway companies are retraining workers for new roles. The industry is becoming more technical and less physical. This creates challenges but also opportunities. Education is emphasizing railway skills. Universities offer railway engineering programs. Apprenticeships train technicians. Countries with advanced railway industries like Germany, France, Japan, and China are exporting expertise. They train engineers from developing countries building new railways. This transfers knowledge globally. Heritage railways preserve railway history but also educate. Museums display historic locomotives and equipment. Visitors can ride on steam trains, experiencing what travel was like a century ago. These heritage railways keep skills alive. Volunteers learn to operate and maintain steam locomotives, preserving knowledge that would otherwise disappear. Railways have shaped civilization for 200 years. They connected continents, united nations, and built economies. They transformed how people live, work, and travel. Railways enabled cities to grow beyond what horses and walking allowed. They made fresh food available year-round. They spread ideas and culture. The railway era isn't over. It's entering a new phase. Railways are becoming cleaner, faster, and smarter. They're essential to fighting climate change. They're making cities more livable. They're connecting people in ways that cars and planes cannot. The trains of tomorrow will be quieter, more efficient, and more comfortable than ever. Railways are more than transportation infrastructure. They're threads that weave societies together. Every journey by train is a small decision for sustainability, community, and human connection. Railways don't isolate you in a car or seal you in an airplane. They let you watch the landscape pass, share space with strangers, and arrive refreshed rather than exhausted. The future is being written on rails. As the world faces challenges of climate change, urbanization, and resource scarcity, railways offer solutions. They move people and goods efficiently with minimal environmental impact. They create economic opportunities. They connect communities. 2 centuries after the first steam locomotive pulled its first train, railways remain vital, relevant, and revolutionary.